Lesson 144, tree diagrams, sample space, and the fundamental counting principle. So we've got 3 things to learn today. The first of them being the tree diagram. And in order to understand the tree diagram, we're going to think of an example. So let's say there is an ice cream shop and a person walks into that ice cream shop. Now, that person has many different options for what they could have as an ice cream cone. So let's say this particular ice cream shop has 2 different types of cones. They have the sugar cone and they have the waffle cone. So the person who walks into the ice cream store first gets to decide, do they want a sugar cone or a waffle cone? Then the person gets to decide what type of ice cream goes into that cone. And this ice cream shop has 4 different flavors to choose from. They have chocolate, vanilla, strawberry, or mint. All right. So the person who is choosing, let's say the person decides on a waffle cone. That's probably what I would pick. I'd go for the waffle cone. All right. So they could go for the waffle cone and then they could decide to choose the flavor of chocolate. Chocolate's a good flavor. However, they could have chosen vanilla, they could have chosen strawberry, they could have chosen mint. So really what a tree diagram shows is all the possible outcomes of a certain situation, or as we're going to see, a probability experiment. All right, so with this tree diagram, you can very easily see that there are in total 8 different options or combinations that this person could have chosen for their ice cream cone. They could have gone for a sugar cone with strawberry or mint, or they could have gone for a waffle cone with vanilla. 8 different possible outcomes. And tree diagrams work with probability experiments. So we've been doing lots with coin tossing. So imagine you started out with your coin toss here. The first time you toss a coin, you only have 2 options. The options are it's going to land on heads or it's going to land on tails. But tree diagrams become useful when you are adding more to the experiment. So let's say you're not just tossing a coin once, you're going to toss it twice in a row. And you want to know what all the different outcomes are for that. So the first time you toss it, let's say you tossed a heads. Then you toss it again, and there are 2 options once again for what could occur after that. So you could toss a heads first, and then the second time you toss it, it could be heads again, or it could be tails. The same thing for the tails. Let's say you tossed it the first time, landed on tails. After it has landed on tails the first time, the options for the second one are heads or tails. So using this tree diagram, we can see that there are 4 possible outcomes. And I've outlined them for you here on a table. So the first outcome is you could toss a heads and then a heads. You could toss a heads and then a tails. You could go the opposite direction. You could toss tails, then heads, and then tails and tails. So there are 4 possible outcomes for tossing a coin twice in a row. And that's what the tree diagram shows. So there's tree diagrams. Our second thing that we have to learn, sample space. Now we've already dealt with tree diagrams. This is just a recreation of the tree diagram I have over there. This is just the list of the possible outcomes if you tossed a coin twice. And a sample space is really just all the possible outcomes in an experiment. And we quite often show sample space using a table. So let's jump down to this table over here. So sample space tables work very similarly to tree diagrams in that they just show you all the different options. So first let's look over here. We've got a heads and a tails over on the left hand side here. What that means is the first time you toss the coin, you have the options of heads or tails. So you'll notice, and you can think of this kind of like a multiplication table, that you've got heads going this direction, and we also have heads going this direction. So if you think like a multiplication table, you can think heads times heads, or in this case, heads and then heads. You end up with 2 heads. Or if you're going from the top, you've got a heads, and then from over on this side, you've got a tails and a heads. So you kind of go where the 2 columns intersect. So let's see, maybe I can undo some of this so it's less messy. Here we go, that works. So if we're looking at the tails, column, the tails row, where those two intersect, tails and tails intersect, we get tails and tails. All right, so it's just a different way to show the same information, and you'll notice that the information is the exact same as we got in the tree diagram, right? We have the same 4 outcomes. Now, sample space tables are useful for experiments where you have more options to keep track of. So let's say you were doing an experiment where you spun 2 different spinners, and you wanted to know all the different outcomes of if you first spun a number spinner and then a color spinner. All right, so let's say you spun the number spinner first, you end up with a, a 1. All right, so let's look at the 1 row over here. You could spin a 1 on the first spinner and then spin a red on the second one. You could also spin a 1 and then an orange. You could spin a 1 and then a purple. Those are all the different options for what could happen if you spun a 1 first. Same thing for the other numbers. You could spin a 2, oops, pen. You could spin a 2 and then a red, a 2 and then an orange, a 2 and then a purple. And for number 3, you could spin a 3 and a red, a 3 and an orange, and a 3 and a purple. So those are all your different options for what could happen if you first spun a number spinner and then a color spinner. And you'll notice that this made it really easy for us to write out all of the different options without missing any. So if you were to just, without this table, look at the 2 spinners and try and list all the different options, it's quite possible, especially as you get into experiments with more and more options, that you might miss one. And then if you don't have it in one of these handy tables, it's tricky to figure out which one you missed. So these are really, really handy for organizing your work and for quickly seeing all the different options and also how many options you have. So for this experiment, there are 9 total outcomes. All right, let's move on to the last thing that we need to learn, and that's the fundamental counting principle. So the fundamental counting principle is the total number of possible outcomes is the product of the number of items in each category. And that sounds kind of complicated, but it's really very simple. So let's go back to our ice cream example. In the ice cream example, we had 2 options for cones. We had a sugar cone and a waffle cone. We had 4 options for ice cream: chocolate, vanilla, strawberry, and mint. All the fundamental counting principle does is if you take the number of outcomes or items in each category and multiply them together, you will get the total number of outcomes. So watch what happens here. We've got 2 cones. We've got 4 ice creams. All you have to do is 2 times 4 to right away know the total number of outcomes, which is what we saw with our tree diagram right at the beginning of this video. So since there are 2 cones, 4 different types of ice creams, the fundamental counting principle just says multiply them together and you know the total number of outcomes, which is 8. Same goes for our spinner experiment, right? We had 3 options on the color. We had 3 options on the number. So all you have to do is 3 times 3 to know that there will be 9 total outcomes, which is what we saw over when we looked at our sample space table. There were 9 outcomes. So the fundamental counting principle is just a little quick way to know how many outcomes you should have in an experiment in total. So all you have to do is multiply the number of outcomes in each category. So you could come to a question like this. Let's imagine you're getting dressed in the morning. You have a red shirt, a blue shirt, a green shirt, an orange shirt, a yellow shirt, and you have black, blue, and beige pants. How many different outfit options or combinations could you make? Well, all you have to do is use that fundamental counting principle. There are 5 shirt options. There are 3 pants options. All you have to do is 5 times 3 to get 15 outcomes. You know there should be 15 outcomes. And then you could go ahead and make either a tree. So you could do red, blue, green, orange, yellow. And then for each of those, you'd have your 3 different pants colors. I didn't really leave enough space. but you get the idea. Or you could make one of those sample space charts where you've got your 3 pants colors. You've got black. I guess I should write them down because they all start with B. You've got black, blue, and beige, and then you've got your red, blue, green, orange, and yellow. And then you can find out the exact different outcomes, all the different outcomes you have. But the fundamental counting principle lets you know there are going to be 15 of them. So that's all there is today. You're going to be working with those 3 things. Let me know if you have any questions.